On July 24, 2001, something from the distant universe sent us a message. It lasted less than 5 milliseconds. It carried more energy than the sun will release in 3 days, and we had no idea what caused it. Somewhere in the observable universe, billions of light years from where you're sitting right now, something fires. No, not slowly, not gradually. In a fraction of a heartbeat, it releases energy so concentrated, so violent, that our most sensitive instruments register it as a screaming spike of radio waves crossing the cosmic void. Then, silence. It's gone before you can blink. We call these events fast radio bursts. And after more than 2 decades of investigation, with the most sophisticated telescopes ever built, with the greatest minds in astrophysics dedicated to solving them, we still cannot say with certainty what they are. But here's what makes them truly extraordinary. They aren't rare. Astronomers now estimate that somewhere in the observable universe, a fast radio burst ignites approximately 1,000 times every single day. 1,000 times every day. So why didn't we find them sooner? Why, when we finally did the discovery feel more like a puzzle than an answer? And what does it mean for physics, for the universe, for us, that these signals exist at all?
The dispersion measure, a cosmic ruler. To understand why these signals were so shocking, you need to understand something counterintuitive about radio waves. When radio waves travel through space, real space, not the vacuum of textbooks, they move through a thin soup of electrons scattered across the intergalactic medium. Those electrons interact with radio waves. And here's the key: they slow lower frequency waves more than higher frequency waves. This means a single burst of radio energy, fired simultaneously across all frequencies, arrives at a telescope spread out, high frequencies first, low frequencies trailing behind. The longer the signal travels, the more spread out it becomes. Scientists call this dispersion, and they can measure it precisely. The measurement, called the dispersion measure, or DM, tells you how much plasma the signal passed through, which tells you approximately how far it traveled. The bursts Lorimer and Thornton found had dispersion measures far too large to have come from within our galaxy. They came from cosmological distances, billions of light years away. Think about what that means. A signal that originated when Earth's continents were still rearranging themselves, before the Cambrian explosion, before complex animal life, crossed the entire breadth of intergalactic space and arrived at a telescope in Australia, carrying enough energy to be detected easily. That kind of energy release doesn't come from something gentle. The energy budget of a single fast radio burst released in milliseconds rivals what our sun produces over 3 entire days. Focused, directed, gone. What in the universe could do that?
Act 1. The Discovery. The Lorimer Burst. The year is 2007. A young astrophysicist named Duncan Lorimer at West Virginia University is sifting through archived data from the Parkes Observatory in New South Wales, Australia. The data is old, collected in 2001, never fully analyzed. Lorimer isn't looking for anything dramatic. He's conducting a survey of pulsars, rotating neutron stars that emit clockwork pulses of radio energy, the cosmic equivalent of a lighthouse. He assigns his undergraduate student, David Narkovic, to process the archive files. What Narkovic finds stops everything. Buried in 6 years of dormant data, a single pulse. Not a pulsar, not interference, not a satellite. A burst of radio energy lasting approximately 5 milliseconds, bright enough to have come from somewhere far outside our galaxy. Lorimer's first instinct is disbelief. The signal was so bright, so brief, so far away, it broke every expectation he had for what natural radio sources could produce. He spent months checking the data, ruling out terrestrial interference, testing every instrument artifact he could think of. The signal was real. When their paper was published in the journal Science in 2007, the astronomical community reacted with a mixture of fascination and deep skepticism. Some called it a fluke, a one-off artifact from an unknown local source. After all, it was a single event, no repetition, no second detection. How could you build a theory on one data point? So the world waited and waited. Then, in 2013, the wait ended. Using the same Parkes telescope, a team led by Dan Thornton published a landmark paper in Science. They had found 4 more bursts, all clearly extragalactic in origin, all sharing a distinctive fingerprint that would become the defining signature of this new cosmic phenomenon. That fingerprint has a name, and it tells us something extraordinary.
Act 2A. Accumulating evidence. Evidence point 1. The CHIME revolution. In 2018, a remarkable instrument came online in the mountains of British Columbia, Canada. The Canadian Hydrogen Intensity Mapping Experiment, known as CHIME, looks nothing like a traditional telescope. No dish, no moving parts. 4 enormous half-pipe-shaped reflectors, each 100 meters long, pointed permanently at the sky, fixed, stationary. CHIME works not by pointing, but by processing. Its digital backend processes signals from across the northern sky simultaneously, using computational power to effectively point in hundreds of directions at once. The results were immediate and staggering. Within its first year of operation, CHIME detected more fast radio bursts than the entire previous history of the field combined. By 2021, the CHIME FRB catalog listed over 500 confirmed bursts. More were detected in CHIME's first year than in the preceding decade. And CHIME didn't just detect more, it found more repeaters, sources that fired not once but many times, different intervals, different intensities. The universe, it turned out, was full of these things. We had just lacked the instruments to see them. Evidence point 2. The galactic burst. April 28, 2020. Something extraordinary happened. For the first time in the history of FRB research, a fast radio burst was detected from inside our own galaxy. The source? SGR 1935-2154, a magnetar, a type of neutron star with the most powerful magnetic field known to exist, located approximately 30,000 light-years from Earth within the Milky Way. The burst was detected simultaneously by CHIME in Canada and the STARE-2 telescope network in the United States. Its properties were unmistakable. In radio wavelengths, it was millions of times brighter than any previously known galactic radio emission from a magnetar. If it had occurred in another galaxy, it would have appeared on our instruments as a classic fast radio burst. For the first time, we had a smoking gun. At least some fast radio bursts were produced by magnetars. For the first time, we had a smoking gun. At least some fast radio bursts were produced by magnetars. But this answer, satisfying as it seemed, immediately opened a deeper wound in our understanding. Evidence point 3. The magnetar problem. Magnetars are extraordinary objects. Born from the deaths of massive stars, they pack roughly 1 to 2 solar masses into a sphere approximately 20 kilometers across. Their magnetic fields reach intensities of 10 to the power of 15 Gauss, 1 quadrillion times stronger than a refrigerator magnet. These fields are so powerful they warp the very fabric of space-time around the star. They stress the neutron star's crystalline crust, and occasionally that crust cracks. When it does, the catastrophic rearrangement of the magnetic field releases enormous energy in milliseconds. A starquake, followed by a massive burst of electromagnetic radiation. This mechanism, confirmed by the galactic event of 2020, explains some fast radio bursts convincingly. But here is where the story becomes deeply uncomfortable. The galactic magnetar burst was millions of times brighter than typical magnetar flares we'd observed before. But it was still thousands of times fainter than the extragalactic fast radio bursts we had cataloged. Meaning, if magnetars explain FRBs, we need magnetars producing events thousands of times more energetic than the most powerful one we've ever witnessed. Possible? Perhaps. Proven? Not remotely. And then there were the repeaters. FRB 121102 didn't just repeat randomly. Analysis of its bursts revealed something deeply strange. The bursts clustered. They arrived in apparent cycles, active periods followed by quiet periods, with a rough periodicity of approximately 157 days. No known magnetar behavior produces 157-day cycles. Then, scientists noticed something even stranger.
Act 2B. Deeper implications. Evidence Point 4. The environment anomaly. When astronomers examined the radio signal from FRB 121102 carefully, they found evidence that the bursts were passing through an extremely dense, turbulent, magnetized environment near their source. An environment so extreme it resembled the region immediately surrounding a supermassive black hole, the kind found at the center of galaxies. But FRB 121102 came from a dwarf galaxy. Dwarf galaxies are small, simple. They don't host the kind of supermassive black hole environments that produce such extreme plasma conditions. At least, they weren't supposed to. Researchers proposed that perhaps the repeating source was a young magnetar embedded inside a supernova remnant, the dense, expanding shell of gas left behind when its parent star exploded. That remnant, still dense with magnetized plasma, could explain the extreme signal distortion. A young neutron star, thousands of years old at most, still energetic enough to produce extraordinary bursts. This model gained traction until a second repeating source was found, FRB 190520, showing the same extreme environment signature. And then more. The pattern was emerging, but the pattern raised a question no one had a clean answer to. If these are young magnetars, where are all the old ones? Why do only some repeaters show these extreme environments? Why do some FRBs appear completely different in their local surroundings? The evidence no longer pointed to a single unified phenomenon. It pointed to something far more uncomfortable. Evidence Point 5. The population problem. As the CHIME catalog grew, astrophysicists began doing statistical analyses of the full FRB population. What they found introduced a new fracture line into the field. Not all fast radio bursts behaved the same. Repeaters and non-repeaters showed subtle but real statistical differences in their burst widths, their spectral properties, their host galaxy environments. A single unified source class should produce a uniform population, but the data didn't support uniformity.
In 2023, a team analyzing the first CHIME FRB baseband catalog found evidence suggesting that repeating sources may be physically distinct from apparently one-time events. Different progenitors, different mechanisms, different histories. Which means the term fast radio burst may be a label of convenience, the way 19th century astronomers used nebula to describe everything fuzzy in the sky, before realizing they were lumping together star clusters, gas clouds, and entirely different galaxies. We may be calling entirely different phenomena by the same name, and building unified theories for a category that doesn't actually exist. The evidence no longer pointed to a phenomenon, it pointed to a flaw in our understanding of reality itself. Evidence point 6. FRBs as cosmic rulers. There is, buried within this uncertainty, something genuinely beautiful. Remember the dispersion measure, the way radio waves scatter through intergalactic plasma? Because FRBs are so bright, brief, and so far away, they pass through enormous volumes of intergalactic medium before reaching us. Every electron in that medium leaves a fingerprint on the signal. In 2020, a team led by Jean-Pierre Macquart at Curtin University in Australia used a sample of localized FRBs to measure something cosmologists had wanted for decades: the density of ordinary matter in the intergalactic medium. For years, cosmological models predicted that roughly half of all the normal matter in the universe, baryons, atoms, existed as a diffuse intergalactic plasma. But direct observations had never found it. It became known as the missing baryon problem. Using fast radio bursts as cosmic rulers, measuring how much their signals dispersed over cosmological distances, the Macquart team found the missing baryons. They were exactly where the models said they'd be, spread invisibly across intergalactic space, invisible to every instrument we had except these millisecond radio pulses from across the cosmos. Fast radio bursts, objects we cannot explain, helped us solve a problem that had puzzled cosmologists for 30 years. The universe had handed us a tool. We still don't fully understand the tool itself. And that leads us to a question so large, so fundamental, that physicists have begun arguing over it at conferences.
Act 3A. Theoretical Framework. The competing theories. Let's map the theoretical landscape because it tells us something important about where physics currently stands. Theory 1. Magnetars. The frontrunner, supported by the 2020 galactic detection, championed by researchers including Vikram Ravi at Caltech and teams at the University of Toronto's Dunlap Institute. Magnetar starquakes and magnetic reconnection events can, in principle, produce enormous radio bursts. The energetics are challenging, but not impossible, if the emission mechanisms are highly efficient. For non-repeating FRBs, catastrophic magnetar events, where the entire field restructures in an instant, remain plausible. Strength, the only theory with direct observational support. Weakness doesn't cleanly explain the highest energy repeaters, the 157-day periodicity, or the population diversity. Theory 2. Compact binary systems. Some researchers, including theorists at the Max Planck Institute for Radio Astronomy, have proposed that periodically repeating FRBs could arise from a neutron star in orbit around a massive companion, perhaps another neutron star, or a massive star with a dense stellar wind. As the neutron star orbits, it passes through varying plasma environments, explaining periodic windows of activity and silence. This model handles periodicity well, but requires very specific orbital configurations to match observations.
Theory 3, cosmic string cusps. Here, the territory becomes genuinely speculative. Cosmic strings, if they exist, are theoretical one-dimensional defects in space-time, relics of the universe's earliest moments, carrying extraordinary tension. When a cosmic string forms a cusp, a point where it briefly reaches near light speed, the resulting gravitational and electromagnetic radiation could, theoretically, produce a radio burst with FRB characteristics. This model was proposed by physicist Tom Kibble and extended by others. No cosmic string has ever been directly detected, but neither has anyone proven they don't exist.
Theory 4, the one scientists don't like discussing publicly. In 2015, Harvard theoretical astrophysicist Avi Loeb, along with Manasvi Lingam, published a paper proposing that some FRBs could be consistent with the leakage radiation from directed energy propulsion systems built by advanced extraterrestrial civilizations. This is not fringe speculation without basis. The paper was peer-reviewed, published in the astrophysical journal Letters. Loeb and Lingam showed that a radio beam powerful enough to accelerate a solar sail spacecraft between stars would, if detected from across intergalactic distances, look exactly like a fast radio burst. The scientific mainstream received the paper with skepticism. Most researchers favor natural astrophysical explanations, as they should. But the mathematical argument has never been decisively refuted. This forces us to reconsider the most basic assumption of all. We are building our theories on the assumption that these signals are natural, but we have not yet proven that.
Act 3B, Future Implications. The next generation of tools. The coming decade will transform our understanding of fast radio bursts, or deepen the mystery further. The James Webb Space Telescope is now being used to study the host galaxies of localized FRBs in unprecedented detail, examining their star formation histories, their metallicities, their large-scale environments. If Magnetar models are correct, JWST should find evidence of recent star formation in FRB host galaxies, since magnetars are born from massive, short-lived stars. Early results are suggestive, but the picture isn't clean. The Square Kilometre Array, the SKA, under construction across South Africa and Australia, will be the largest radio observatory ever built. When fully operational, it will detect FRBs at a rate of potentially thousands per day, with localization precision far exceeding anything currently possible. With thousands of precisely localized bursts, statisticians will be able to map FRB distributions across the universe, testing whether they trace star formation, galaxy mass, dark matter density. What solving this mystery actually means. Consider what happens in the two most likely scenarios. Scenario A, FRBs are purely natural astrophysical phenomena.
If magnetars, or compact binaries, or some other natural engine fully explains every fast radio burst we've detected, then we are surrounded by objects so extreme, so violent, so far beyond anything in human experience that they make our physics textbooks look like rough drafts. Magnetars alone, objects that can release 3 days of solar energy in 5 milliseconds, represent a class of phenomenon for which we have no complete physical theory of emission. We don't know exactly how the radio waves are generated. We don't know what geometry produces the beam. We don't know why some are more efficient than others. And if FRBs reveal that the universe hosts multiple distinct, ultra-energetic phenomena that we've accidentally collapsed into one category, then we have serious systematic errors in our cosmological measurements, including our use of FRBs to measure the missing baryons, including our use of them as cosmic rulers, which means some of our most elegant recent results may rest on assumptions we haven't fully justified. Scenario B. FRBs have a component that is not natural. This isn't the mainstream view. It is not what most scientists believe, and there is no positive evidence for it. But if even a fraction of FRBs, even one, is shown to carry a non-random, structured, information-bearing signal, the implications are beyond the scope of any single scientific paper. We are not saying this is likely. We are saying the question has not been closed, and that is a distinction that matters enormously. Act 4. The ultimate questions. What FRBs reveal about our place in the cosmos? Step back for a moment. Not from the data, not from the theories, from the scale of what we're discussing. Right now, in the time it takes you to finish this sentence, approximately 3 fast radio bursts have erupted somewhere in the observable universe, each one releasing unimaginable energy, each one invisible to your senses, inaudible, undetectable by any organ evolution gave you. They have been crossing the cosmos for billions of years. They were erupting before Earth existed, before the Sun existed. They will erupt long after our star has burned to a cold white dwarf. And we only discovered them in 2007, not because they weren't there, because we weren't listening. This raises a question that cosmologists rarely state plainly, but that hangs over every FRB conference, every new detection, every paper published on the subject. How much of the universe are we still simply not listening to? The dispersion measure gave us the missing baryons. What other cosmological measurements are we making incorrectly because we're missing a signal source we haven't discovered yet? Every time astronomers have opened a new observational window, X-rays, gamma rays, gravitational waves, they have found phenomena no theory predicted. Pulsars, gamma ray bursts, black hole mergers, magnetar flares. None of these were anticipated before the instruments existed to detect them. Fast radio bursts followed this same pattern. We opened a new window. Something looked back. The problem of consciousness and scale. The most profound implication emerges when we consider this. The universe has been producing these events for the entirety of cosmic time. Fast radio bursts in the early universe, billions of years before any star had died and returned its metals to space. Billions of years before rocky planets could form. Billions of years before chemistry could organize itself into cells. For most of the universe's 13.8 billion year history, these bursts erupted, crossed intergalactic space, arrived at Earth, and were absorbed harmlessly by the atmosphere, unheard, unnoticed. It took the universe nearly 10 billion years to produce a species with instruments sensitive enough to notice. And even then, we almost missed it. The Lorimer burst sat unexamined in an archive for 6 years before a student happened to look. How many other messages, natural or otherwise, have already passed through us unread? Physicist Freeman Dyson once wrote that the universe is not indifferent, it is, in some sense, expecting us to notice. Not in a mystical sense, in a purely physical one. The laws of physics are such that matter, organized at sufficient complexity, can perceive the universe's most extreme events. Fast radio bursts are one of those events. We are now, barely, organized enough to perceive them. What we do with that perception is the only question that remains entirely in our hands.
Concluding this journey of exploring FRBs with me, Akash, the one who runs Cosmic Ledger, we began with a signal. 5 milliseconds, enormous energy, unknown origin. We followed it across 3 billion light years, through dead stars and plasma clouds, through colliding neutron stars and cracking magnetic crusts, through competing theories and incomplete data, and the beautiful mess of real science in progress. Here is what we know. Fast radio bursts are real. They are among the most energetic events in the observable universe. They are common, happening thousands of times every day across the cosmos. Some repeat, some don't, and that distinction may be the deepest clue we have. The 2020 galactic detection gave us our first confirmed source, a magnetar. But magnetars alone don't fully explain everything we've seen. The population is diverse, the environments are strange, the periodicities are unexplained, and the dispersion measure, the very thing that makes FRBs hard to understand, turned out to be a ruler that solved a 30-year-old cosmological mystery. Here's what we don't know. What produces the most energetic repeating bursts? Why the burst windows cycle with periods of months? Whether all FRBs share a common origin, or whether we've been grouping entirely different phenomena under a convenient name. And perhaps most importantly, whether the universe's most powerful radio transmitters are telling us something we haven't yet learned to read. The SKA will come online. JWST will map the host galaxies. Einstein telescope will listen for gravitational waves. And somewhere in British Columbia, the CHIME telescope is watching the sky right now, waiting for the next burst, waiting for the next clue. There are 1,000 signals crossing the universe at this moment. We are just beginning to hear them. The universe does not owe us simplicity, but it has at least agreed to speak.